We need a tool, a technical tool, to transform one set of vectors into another. So let's say you have a set S of vectors, and you have another vector Z that you want to inject into the set S. But you want to maintain that S has the same cardinality, so you have to eject another vector from S. And you want to do this in such a way that you don't change the span. Well, the exchange lemma is a technical way of achieving that. It tells you which vector to eject. We'll start with a simplified version. So here's the simplified exchange lemma. Suppose S is a set of vectors and Z is a non-zero vector in the span of the set S. Then there always exists another vector W in S such that the span of the set obtained from S by adding Z and removing W is the same as the span of S. That is, W is a vector we can remove while maintaining the same span. Here's how the proof goes. We write S as the set consisting of V1 through Vn. Now, since Z is in the span of this set S, we can write Z as a linear combination of the vectors in S. By the superfluous vector lemma, the span of the set with Z is the same as the span of the set without Z. Now, since Z is non-zero, at least one of the coefficients in this representation is also non-zero. Say it's alpha I, the coefficient of Vi. Well, we can rewrite this by moving everything over except for alpha I times Vi. And now we divide through by alpha I, which is guaranteed to be non-zero. And we manage to represent Vi as a linear combination of all the other vectors. Using the superfluous vector lemma, therefore, the set spanned by S with Z is the same as the span of the set S with Z but not W. And that proves this simplified exchange lemma. So we see that the simplified exchange lemma is not enough. We need to enhance this lemma. We introduce a set of protected elements, A. Here's the full exchange lemma. Suppose S is a set of vectors and A is a subset of S. Suppose Z is a vector in the span of S such that the union of A with Z is a linearly independent set. Then there's a vector W in S and not in the protected set A such that the span of S is the same as the span of the set obtained from S by adding in Z and taking away W. You see that, unlike the simplified lemma, we require not just that Z be non-zero, but in fact that the set A union Z is linearly independent. So here's the statement of the lemma. Let's go through the proof. We'll write the set S in this way. V1 through Vk followed by W1 through WL, where the set of protected elements, A, consists of V1 through Vk. Now, since Z is required to be in the span of S, we can write Z as a linear combination of the vectors in S. Here's a linear combination. Z is alpha 1 times V1 up to alpha k times Vk plus beta 1 times W1 up to beta L times WL. By the superfluous vector lemma, span of the set obtained from S by adding in Z is the same as span of S. Z is a superfluous vector. Now, if these coefficients beta 1 through beta L were all 0, then we would have written Z as a linear combination just of the vectors V1 through Vk. But that would contradict the fact that A together with Z is a linearly independent set. So at least one of these coefficients, beta 1 through beta L, must be non-zero. So let's say beta 1 is a non-zero coefficient. Then we can rewrite this equation in this way by moving everything from the right-hand side to the left-hand side except beta 1, W1. And we get this equation. Now we divide the whole thing by beta 1. We can do that because we know beta 1 is non-zero. And we get this equation, which expresses W1 as a linear combination of all the other vectors. Therefore, by the superfluous vector lemma, the span of the set S together with Z is the same as the span of the set S together with Z with W1 omitted. And that completes the proof. Now I'll show how the exchange lemma can be used to prove that our minimum spanning forest algorithm is correct. This is not really part of linear algebra. I'm doing it just as an illustration of the power of the exchange lemma. Here's the algorithm, remember, for finding a minimum spanning forest of a graph G. We start by initializing the forest to the empty set, and we consider the edges in increasing order of weight. For each edge E, if E's endpoints are not yet connected, we add E to F. We'll show that this algorithm, this greedy algorithm, actually finds the minimum weight spanning forest. And let's assume for simplicity that all the weights are distinct. Here's how the proof goes. Let F be the forest found by the algorithm, and let F star be the truly minimum weight spanning forest. We want to show that F is equal to F star. To do that, we'll use proof by contradiction. We'll assume for a contradiction that they're different. Now, let E1, E2, and so on up to EM be the edges of G in increasing order of weight. Now, let EK be the minimum weight edge on which F and F star differ. Now we have to set ourselves up to apply the exchange lemma. Let A be the set of edges that occur before EK in this order that are in both F and F star. Since at least one of the forests includes all of A and EK, it must be that A together with EK has no cycles. It's a linearly independent set. Now consider the moment where the GROW algorithm is deciding whether to include EK in F or not. So far, the algorithm has chosen the edges in A to be included in its forest. Now, we already said that EK does not form a cycle with the edges in A, so the algorithm must choose EK to put in the forest F. Now, since F and F star differ on EK, it follows that F star does not contain the edge EK. Now we can use the exchange lemma. A is a subset of F star. A together with EK is a linearly independent set. Therefore, by the exchange lemma, there's an edge, call it En, in F star, but not in A, the protected set, such that the span of F star together with EK, but not including En, is the same as the span of F star. That shows that this set, where we replace En with EK, is also a spanning set. But when we did that replacement, the set got cheaper. EK occurs earlier in the order than En, so it has smaller weight. That shows that, in fact, F star must not have been the truly minimum weight spanning forest after all. That's a contradiction, which completes the proof.